Hello, my name is Brock LaMeres, and I will be your instructor this summer in EELE 367 Logic Design. In this video, we're going to go over the course and discuss the logistics of how it's going to look, what you are going to do, how you're going to turn in assignments, and just the overall programmatics of the summer. And then what we're going to do is I'll give you an overview of the class, and then I'll give a little bit of background on myself as the teacher and also the author of the textbook and the voice and hands that you'll see and hear on the videos.
So let's begin with what this course is all about. And to do that, sometimes it helps to take a look at the prerequisite for this course to put it in context of what we're trying to accomplish. So the prerequisite is a course in digital logic circuits. That could be either EELE 261 at Montana State or an equivalent class at another school. But the goal of that was to start looking at the basic building blocks of a computer. And so we're looking at the hardware and we're looking at the very low level. So like AND gates and OR gates and stuff like that. So very, very low level. And to do that, we had to start with looking at like, what is a digital signal to begin with? What is this whole thing of ones and zeros, and how do we interpret voltages to be that, either a logic high or logic low? Then we said, well, if we're messing around with ones and zeros, we got to know number systems. So we got to understand the binary number system and how to perform arithmetic and how to represent information with that. Then we had to look at the digital circuits. So if we're going to build circuitry that manipulates ones and zeros, we have to go down and look at what is it? What is an AND gate? What does it really look like? What kind of voltage levels does it use, power supplies, etc. And then we looked at, well, okay, now I'm going to do combinational logic design, which means if somebody gives me a truth table, I need a process to synthesize the circuitry. And so we looked at K-maps and build, and minimization, logic minimization, and sum of products, product of sums, architectures, and all that sort of stuff. But it got us to the point where we were able to take a functional description of a circuit in the form of a truth table, and we were able to actually create a gate level schematic and implement that on a breadboard. And that was pretty cool. But then we also said, geez, man, this is really tedious. The designs get big really quick. So we introduced Vhdl, a hardware description language, which allows us to basically describe the circuit functionality we want in text, and then allow a tool such as a synthesizer to actually crank through and create the gate level design for us. And the reason that was really neat is because we could actually simulate the functionality prior to actually building the circuit. So we could figure out if we had errors in our logic. So then we use that to explore larger combinational logic circuits, such as MSI logic. So that's like decoders and multiplexers. And then finally, we learned about sequential logic, which is building finite state machines. And that is that circuitry that produces outputs based upon where you are in terms of the inputs and where you've been in terms of the inputs. So we had this notion of storage in the form of D flip-flops, and the D flip-flops were able to track history by having a sequence of states that represented where it's been. Okay, so then that brings us to this course, which is called Logic Design. And so what is logic design about? Well, we're still looking at the basic building blocks of a computer. The only issue is that to get to the end where we can actually build a computer, the next ones are going to be pretty big. Okay, so it's no longer, well, should I use Vhdl or should I use a K-map? The answer is you're done with K-maps, okay? So we're now going to use a hardware description language for everything going forward. So the next modules, we actually are going to do module 8, 9, 10, 11, 12, and 13. Now you're like, why is you not starting with module 1? Well, actually, this is a continuation of my book, Introduction to Logic Circuits and Logic Design. Notice that the first class was Introduction to Logic Circuits, and this class is called Logic Design. So that's why where the title of the book came from. It's the two classes that I teach put together. So module 8 is chapter 8 in the book. And so we immediately start with saying, well, we learned a little bit of VHDL, but I need some more advanced techniques to model big stuff. And so we go to VHDL part 2. And this is where we look at things like a process within Vhdl that allows us to trigger signal assignments instead of just having them happen immediately as soon as there's a change on the input. And that opens up things like if-else statements and case statements. And we look at how we can build finite state machines with that. And we look at how we can model all different types of different circuitry. So then module 9 is where we go back and we start looking at it. Let's go ahead and model some of these larger combinational logic circuits and even sequential logic circuits using the techniques that allow us to go big. So some of these techniques that come from Module 8 VHDL Part 2. So this is where we go back and we're using if-else statements and case statements to build big decoders and stuff like that. Then we go and change gears quite drastically, and we look at how to build a memory system. So we no longer use D flip-flops to store information. We're actually going to build memory arrays. So we look at the technology and the architectures used to build ROMs and read-write arrays, and then we build that in VHDL, and it turns out that these are absolutely synthesizable. And then we turn our attention very quickly to programmable logic. So since we are now going to be implementing everything on the FPGA, we already are doing that, but we've kind of glossed over what it is. We're just like, don't worry about it. It's just a programmable logic device. Put your VHDL on there, and trust me, it works. Well, now it's time. We can't do that anymore. We need to be owners of the hardware. So we actually go and look at what is an FPGA. And to do that, you have to kind of look at what was the history of programmable logic that led to the development of an FPGA. And once you get to that point, now you're sitting there going, okay, now I'm getting good at digital design, because I'm not just throwing VHDL down, hitting synthesize, and hoping it works. It's like I know where the gates are going. I know they're going into lookup tables on this FPGA, and I know what an FPGA is. Then we turn our attention back to arithmetic circuits. And so this is where, instead of using like combinational logic, explicitly to do an add, we start using the plus sign, and we start using the minus sign, and we start using, higher level modeling techniques to implement these arithmetic circuits. And that then culminates with the granddaddy, which is Module 13, where you will build an entire 8-bit computer in VHDL, and you will program it by putting opcodes and operands in the program memory and running it. This module is the culmination of both classes, where you have learned all the pieces that go into a computer system. You know how each works, and then we bring them all together and learn how to build the most ubiquitous technology there is on planet Earth, which is the microcomputer. And so this hopefully will be the light bulb moment that really brings everything together that you've learned in logic. And you understand, it's like, wow, I've written hello world, and I hit compile and it works, and I have no idea what is going on in the hardware. Now you're going to be like, wow, I understand what the hardware is doing. So before we get into the logistics of the class, you must be wondering, well, who is this guy who's going to be teaching me about these building blocks? So I am a professor of electrical and computer engineer at Montana State University. So I am physically located in Bozeman, Montana. And I got my bachelor's degree from Montana State back in the 90s. And then I went to work for Hewlett Packard, where I designed electronic test equipment for 8 years. And I was a digital hardware designer. So I did FPGA design, printed circuit board design, acquisition system design. And so all of the circuitry that I'm going to be teaching you about is stuff that I actually use as an engineer in industry. And so this stuff is real. It's not just make believe. You will actually use this stuff. And so while I was working at Hewlett Packard, I decided to go to graduate school. So I went to, I got my master's degree at the University of Colorado in Colorado Springs. And then after that, I started teaching as an adjunct instructor, classes on embedded systems at University of Colorado in Colorado Springs. And after a couple of years of that, I decided that I really liked teaching, and I really liked being an electrical engineer and a computer engineer. So I decided to go back to school and get my PhD. And so then I continued working and going to school, but this time I was going to school at the main campus at University of Colorado in Boulder. And so then after years went by, and I ended up getting my PhD, and that allowed me to become a professor. So in 2006, I came back to Montana State, and I have been a professor now for nearly 15 years. And what I do is I teach and do research in the broad area of computer engineering and digital systems. And so I'm showing you my website right here just to kind of highlight some of the things that I do. So the classes that I teach are like Introduction to Logic Circuits, obviously, both at the very low level all the way up to senior and graduate level, digital system design and high-speed digital system design. And then I do research on, using embedded systems to solve problems and also coming up with novel computer architectures for various applications. So my main work, if I come out to my research over here, my main work has centered around trying to exploit these programmable logic devices to create real-time adapting hardware that can recover from faults
or give you better performance in real time. And so most of my work has been funded by NASA. I currently have a project right now where I'm building a computer that's going to go to the moon in 2022. I've got we actually have this computer that we've invented called RADPC that uses an FPGA and can react to ionizing radiation that causes a normal computer to crash. And so we've developed this computer and we're going to fly it, or we actually have 2 small satellites in orbit. One of them is called RadSat-U. This is a picture of it right here. This is its launch back in November of 2019. I'm standing in this crowd right here with my students watching that go off from Wallops Flight Facility. Here's a picture of it being pushed out of the International Space Station, so it's in orbit right now. We have a second satellite that's up there called RadSat-G, and these things are about the size of a loaf of bread. Here's its pictures of it. It's launched at night, being pushed off the International Space Station again. And then we do all sorts of other things like balloon flights to try to test this computer in various environments. We've had it on the International Space Station. Here's a version of this computer, RadPC, being installed by an astronaut. And then we've done everything from flying on sounding rockets to weather balloons. And so anything and everything to just kind of test that technology. So what my background brings is I have a degree, a PhD in electrical and computer engineering. I've also worked in industry using this stuff. And then I also do research that really takes what I'm about to teach you and actually implements it in applications that can kind of advance computing technology. Okay, we are now ready to actually look at the course. Okay, so the course logistics. So it all starts with this learning management system called Brightspace. So this is the website for the course, and this is where you find everything that you're going to need to do everything. This is where you find the assignments. This is where you do multiple choice quizzes. This is where you upload videos of your laboratory assignments. This is where you find everything. So you go out to the address ecat.montana.edu, and it'll redirect you to ECAT1 or ECAT2, but it's just type ecat.montana.edu. And when you come in here, you're going to log in with your net ID. And so your net ID and password are what you were assigned when you basically registered as an MSU student. And when you come into here, you're going to see the launch site for Brightspace. But when you scroll down, you're going to see your courses listed over here. So here's your active courses, logic design. So here we are. I put a welcome message that shows up here just so that you know you're alive and kicking. But when you click on your course, it will also show up here. And so I just have this announcement here. It's just to reassure you that when you come into this class, you're in the right place, And so it's like, welcome, here we are. Here's the cover of the book. And you can start working through the material. Okay, so I have a little link right here that'll take you to the first content page, which is the course information and syllabus. But to show you kind of how else to navigate this course, up here is all the tools that are available in Brightspace. We're not going to use all of them, and I have linked everything in content. Okay, so for example, if I go to content, this is where you really should go every single time you come into the Brightspace shell. And if you come in, you're going to notice that there's really only one folder. There's the course activities. And if you look at this, you basically are going to see a page for everything we're going to do in the class, and that consists of overview of the course, and then here's your modules, module 8 through 13. And you come into these modules, and they are going to have the activities that you will do to accomplish that module. So let's start with course information and syllabus. So this is kind of like just going over the regular syllabus. It's kind of a quick summary of what's in the real syllabus. And I do that so that you can find links to like contact information. So you come in here, it's like, hey, I'm in logic design. Welcome, this is the Brightspace page. And I do have a link right here for the course syllabus. And so if I click on that, we'll go through that. That's the detailed syllabus. And you want to have that handy throughout almost every single day because it has the deadlines. But you're going to see down here, it's like, here I am, call me Brock, here's my contact information. Our teaching assistant is Stephanie Smith, and so together we're going to work through this summer session and help you. And I should note right away that the preferred mode of communication is email, okay? And so what we'll attempt to do is respond to you within 24 hours, if not sooner. And we need you to get in gear with using professional email etiquette. And so what I do is immediately, I have a little opportunity for you to, before you even start the class, to just gain extra credit. Okay, so I'm going to give you 20 points of extra credit if you read through this little email etiquette guide that I wrote. And at the end of it, it'll ask you to send me an email with
properly written message. So nothing where you send it to me and you don't address it to me and you don't sign who you are and your email is horrible. Your email address is some stupid email address that you made up when you were in high school, and I don't know who you are. I don't know if you're trying to talk to me, and you know, it's just garbage. So I want you to start emailing using the form in here, and to incentivize that, I'm just going to give you free points. Okay, so I'm going to give you an extra 2% on your overall grade. That could mean the difference between a B and an A. Okay. So anyway, go ahead and look at that right away. And then here's the required material for the course. Number one, you're going to need a computer with internet and running Windows. This is the moment. I'm sorry. If you have a Mac, it's over. You can't run our software on a Mac. So if you have a Mac, you either need to go get access to a Windows machine, or unfortunately you need to drop the class. I've tried this for years to help people with dual boots. Some people can get it going. If you can get a dual boot going on your Mac, that's fine. I've never used a Mac. I don't want to use a Mac because engineering software doesn't run on it. So I'm sorry, just if you have a Mac and you don't know how to get Windows on it, you got to drop the class. Okay, so I apologize for that. Okay, the next thing you need is a textbook, Introduction to Logic Circuits and Logic Design with Vhdl. So second edition is out. If you have the first edition, that's fine too, or if you can find the first edition, that's fine. The book is in the bookstore, but honestly, Amazon has cheaper prices, and you can get used ones on there. So just get access to that book. Then you're going to need the Digital Logic portable lab kit, and this is another moment where you need to sit there and go, "Oh, what's a Digital Logic portable?" Or, you know, what's this portable lab kit that Brock's talking about? This is where you need to go look at your email, because I've been emailing you for now a week asking for an address to ship you your kit, because you're going to need that kit on day one, because you start off right away doing designs. And so please go check your email. If you can't find your email because you haven't worked through the professional email etiquette guide, send me an email because I need you to get this kit. If you're in Bozeman and can check it out, you just come over to Cobley Hall and grab one. But this is key. You need this kit. No, you ask what's in the kit. It's an FPGA board. So you're going to have an FPGA that you're going to design VHDL and download everything to it. So every lab is done with the portable lab kit. And then you need a camera capable of taking short videos. That's how we do the lab demos. We're not doing live WebEx or Zoom to do demos. You're going to actually create a little video of your demo, and you will then upload it to an assignment folder. Okay, so we'll go through that. We'll talk details in that a second, or more details in a second. So I'm going to click on the course syllabus, and here's more details on what's going on. But the most important part of the syllabus is going to be the schedule. So let's kind of walk through this. You know what the course is. Here's your learning outcomes. This class is based on how to teach you how to do something, not just to make you feel good. Contact, required information, blah, blah. We already talked about that. Prereq, you need to have 261 or an equivalent class. Everything's fine. Everything's fine. Now we get down into what the activities are. So here's your grading distribution. You're going to have weekly homework, labs, end of module quizzes, and a final project. The final project is module 13. That's the computer. Okay. Notice that's a big boy right there. That's 20%, right? The way that I do the points is there's 1,000 points available, and each assignment is worth points. So you can just watch your point total accumulate up until you get the grade you want, and you're done. The grading scale is I'm a straight grader, 90 and above is an A, 80 and above is a B, etc. I usually don't use pluses and minuses, but I reserve the right to in case I need to. Okay, academic policies, this is the don't cheat thing. You're in an online environment, and sometimes the online environment is interesting because you're alone. A lot of times you're alone, and so you can't really cheat. But let me tell you what cheating is, okay? So cheating is not collaborating. Cheating is where you turn in somebody else's work. In engineering, everything you do is collaboration. Okay, so if you work with other people, that's absolutely fine. That's how everything gets done. The difference becomes when you just walk up to somebody and say, "Look, I can't figure this out. Can you just give me your VHDL?" And then you upload that as your own. So that's cheating. So work together if you are together. But at the end of the day, every single student in this class has to do their own work, like type in their own VHDL on their own computer on their own FPGA board. And they have to upload their own assignments, okay? And that can look interesting when you're collaborating because you have two people that are on separate computers kind of doing the same thing, but that's fine. That's how it's done. All right, what are the activities? What do they look like? Well, you have reading and instructional videos. So remember, this course was designed, basically I evolved this course over time to be what it is right now. and which is, I think represents an approach that gets you ready for industry with real skills and with all the background you need, so that you just don't jump to the end and say, I don't know, I'm just writing a program and hit a button and I have no idea what's going on. It's like, you know what's going on by the end of this course. So I developed the course, then I wrote the book. So it wasn't that I had a book and then I tried to make a course go around it. The book was written after the fact to be a resource for the class. So what that means is that we follow the book exactly. So you're going to read chapters 8 through 13 in the textbook, and we do every single exercise, every single example. We walk through the material just sequentially, and when you're done with chapter 13, you're done with the class. But to go along with that, what I did is after I wrote the book, then I went back and I recorded YouTube videos that are short videos corresponding to the sections in the book. So you kind of have two modes of getting the information from me to you. And some people like reading, some people like videos, some people like both. And so it's kind of up to you what mode you want to learn with, which one you're more comfortable with and which one's more efficient. And so they're both available to you. Okay, so then here comes your graded parts. So you're going to have homework. Homework is always going to look like either a multiple choice quiz in Brightspace, or, and I say it's a quiz because that's the tool name, so it's just a multiple choice format assignment, or you're going to do simulations. So you're going to use Model Sim, which is part of the software that we use, and you're going to do these VHDL simulations, and you'll take screenshots of your simulation waveforms, and you'll upload that to the assignment folder, or you'll upload your VHDL. And so then we look at those and then we assign a grade. Quizzes, or the multiple choice ones, get graded automatically and you see your grade right away. But that's what the homework consists of throughout the semester. Here comes laboratory. So you say, well, how do I do these labs? Well, you're going to have this FPGA board sitting in front of you. You're going to have Quartus and Model Sim and yeah, you're going to have Quartus sitting on your computer, and that's a free software. And you're going to design programs or design circuitry that matches the lab handouts and see what I'm requesting. And then you're going to take a short video of it. And so you're actually going to pull out your phone. And what I want you to do is I want you to start with a shot of your face and say, hey, this is LaMeres, well, your name, and then show me what's going on. And it's remarkable how easy these are to demo, because really a lot of them are just, you have the FPGA board and you're going to be changing switches and making LEDs blink, or you're going to have like a counter running where it's incrementing, the 7-segment displays on the FPGA board. So it really does only take about 5 to 10 seconds to demo these things. And right away, after you grade enough of these over time, it's like I can look at these, and Stephanie can look at these like immediately and be like, yep, that's working, or nope, you have an LED out. And so that's how we're going to do the demos, okay? And then at the end of every module, we're going to have a module quiz. And this is going to try to represent like what it would be like if you were live and you had to do an exam. So you come into class and we're going to do an exam. So these are all online multiple choice quizzes that basically are a summary of the module. So the difference between like a homework multiple choice quiz and a quiz is that the module quizzes are timed. So this is like you come into class, you have a half an hour to complete this written exam, and then you got to leave. That's how these are. Now these quizzes, module quizzes have deadlines. It's just that once you start them, there's a clock that runs. So you can start it anytime before the deadline. It's just that once you say go, even if you log out of Brightspace, the timer still runs. And once your timer goes out, then it's done and you get your grade that you did. So be careful when you start these. Make sure that you, number one, do them before the deadline, but make sure you're ready to do it and you have allocated time. Homework's different. Homework's going to have a deadline, but you can open it any time. You can open up all the homeworks for the whole class right now and look at them. And you can save answers, and they only get submitted when either you hit submit or when the clock runs out. The deadline runs out. So there's no clock. You can have these open for, the whole week, or if you're looking at ones in a couple months, you can have them open for months. So that's the main difference. And then the final project is going to be the computer. And so you're going to have all sorts of stuff for this. There's going to be a couple multiple choice homework kind of ish things that you get grades for. You're going to have incremental VHDL that you turn in. You're going to have incremental FPGA demos, and then you're going to have like this choice at the end where you say, I want to implement more and more instructions on the computer, and that'll make sense once you get to the computer. And so then that's going to be what the big grand finale is. Here is what you need to have in front of you almost every single time. So here is every single graded component of the class, and here's the exact flow we're going to do. This is broken down by week, and so when you log in, week 1, May 18th, you start off and it's like, here's exactly what I'm going to do. I'm going to march through these, and the pace that you march through them is up to you based upon these deadlines. So right away, you have an assignment due on Wednesday of the first week, and that is to do a multiple choice quiz on homework 8.1, and it's worth 3 points. And then you're going to do a VHDL simulation, and that's worth 12 points, and they're both due on Wednesday. And it's really quick because we got to get going. And this will force you to get the software installed. So that's why this one's right there, because you need this software because we're going to do so much VHDL. So you're going to install this Quarta software, and this is in like the handouts for the homework, right? Okay, and in videos. And then what happens is from then on out, every deadline is due on Wednesday at noon. Okay, so if you look at this, the first week you have a couple assignments that are due during the week, and that's to get you going. And then from then on out, the weekly activities are due the following week at noon. So week 2, you do a couple things. You have your first, you have a lab during week 1. It's due the next Wednesday at noon. Now you come into week 2, here's what you're going to do. You're going to do this homework. That's a simulation. You're going to do this. It's a lab, and you're going to do the end of module quiz. They're all due the following Wednesday at noon. And if you go through these, you just see everything's due the following week at noon. You're just marching through these in sequence, and you just keep building up points, building up points, building up points, building up points. Finally, you get your A, you're done. You know how logic design works. So this is key to always open this up and make sure that you know what's happening. Okay, so now let's take a look at what a module page would look like. So if I come over, I can click this arrow to go to the next one, or I can go to content and click on it. But here's like what every module page looks like. I'm going to tell you what the module is, what the learning outcomes for it are, and then here's your activities. So everything is broken down into a section of the book. And so here we go. Section 8.1 is the process. And so you're going to read this or watch the video. And what's the video? You click on that. It's a YouTube video of me talking about the process. And then you do a homework. And now sometimes when you click on the homework, if I click on this, it'll either bring up a quiz. This one happens to be a quiz, and I can start the quiz. So I'll start it. And then, so this would be exactly what you're going to be seeing. So it's like, oh, okay. When using a sensitivity list in a process, what will cause the process to trigger? And it's like, I don't know. Well, I'll do these. So then you click all these, and then you submit it. If you don't, let me just plunk an answer in here. I don't know if that's the right one. I'm not really reading right now. But let's say that I did that and I didn't want to submit. I just go ahead and hit the back arrow, right? And then it basically says it's saving the quiz, and it's taking me back out of the, notice that it's saved right there. And so I'm like, all right. Actually, I guess you hit close. So I close that, and there you are. So now if I come back to the activities, that was an example of a homework that was a quiz. Let's look at one that's a homework for a VHDL. Here comes section 8.2. So you read or watch these videos, and then you come down here and you click on homework 8.2, and you're like, oh man, this is a different one. Well, this right here is a VHDL simulation assignment. And so I describe what it is. Notice everything's out of the book. So this really is a problem out of the book. And then it gives you any information you need. So here's a test bench that you're going to use. You save that. You design a circuit that does this truth table using if-else statements, if-then statements. And then you're like, I'm all done. I got my simulation. What do I do? Down here at the bottom, you are going to see your deliverables. So you need to do a screenshot of your simulation, name it exactly what I need, and then go ahead and upload it to the assignment folder. And the assignment folders are essentially just places you can upload information. So you add a file, and you go find your little files, upload them, and then once they go in there, we grade them. And when you look back at the little deadline thing, then we go in and we grade it, and it's like, oh, okay, 12 points can be assigned. I look at it, or Stephanie looks at it, and we assign your points. Okay, and as you go down, you just march. At the end of every one, there's a quiz. Okay, so remember, you got to get that quiz. And then you just go through this class, boom, boom, boom. And so there it is, but module 9 looks very similar. Module 10 looks very similar. And it's laid out exactly in a sequence of events until you get the points you need. Okay, so that's the logistics of it. Hopefully it'll be very straightforward. I'm going to send emails periodically throughout the week to kind of make sure that I'm checking in with you. And so now I'm going to end with this. I'm going to give you some tips, okay? First and foremost, this class is a 12-week summer session class, and that corresponds to approximately 10 hours of work each week. Okay, so that's what I've historically found in this kind of format. This is a credits semester-based class that is being offered in 12 weeks. So what it's come out to be, honestly, is it's about 10 hours a week. So it could be more, could be less. If you want to just space it out evenly, that you should be fine with that. The key to this, though, is don't make those 10 hours like Sunday night starting at 7 p.m. and you just try to go through the night. That is the worst way to learn. The best way to learn this and the best way to stay engaged in online learning is to do periodic check-ins. So I recommend that you log into Brightspace 5 times a week and do something, whether it's read, watch a video, but just stay engaged. And you'll learn a lot better if you check in more frequently and do shorter activities than trying to do some marathon once a week right before the deadline. So try to do a minimum of 5 logins per week. When you log in, I always go to the syllabus and look at the schedule and think about, where am I? What am I doing this week? When are the deadlines? And where am I in this process? Okay, so this is how you succeed. The next thing, check your email. You got to check your email because I'm going to be sending you reminders. I'm going to be asking you questions on how things are going. That's how you're going to ask for help initially. We can set up video calls and we can help you debug your code and everything. But it's amazing how easily it does work if you email me your Vhdl and email Stephanie your Vhdl, and we just look at it and be like, yeah, you semicolon. You know, it's pretty easy. Now here's the final one that I'll give you. Don't stay stuck. Okay. What I mean by that is the worst thing that could happen in an online learning environment is where you're stuck on something, you can't see the answer, and you feel like you just need to stare at it longer. And the hours go by, and then all of a sudden it's 2 hours, then it's 4 hours. Now you're sitting there at 8 hours staring at a VHDL, and you cannot figure out what it's done. You've compiled it 1,000 times, and then I get the emergency email at midnight that says, "Oh, model sim's down, VHDL doesn't work anymore. You know, they deleted VHDL from the IEEE library," or just all these crazy emails that I get. So those only happen when you've stared at something for too long. So my tip is only stay stuck for about a half an hour. So if and that requires you to think about what you're working on at that moment. So you work through these activities and you need to be aware of, am I progressing? Okay, so I'm working through these things. I'm watching videos, I'm doing homework, I'm doing simulations, I'm watching videos, I'm reading. Are you making progress toward the end of the week's activities? When you are, then you just keep working and life is good. You say, I have a goal today to get done with 8.1. You did it. Life is good. I have a goal tomorrow to work through 8.2. It's when you notice that you're not progressing and you're staying on a topic for way too long, and the way too long is about I'm half an hour with no progress. Then you need to log out of Brightspace and do something else. So that's either go to sleep, that's either change to another topic, do something else, or reach out for help. And so you need to, it's kind of on this is self-regulation theory, right? It's up to you to track what you're working toward, where you're at, and if you're spending too much time stuck. And that's where you can reach out for help and just change gears. A lot of times, if you just take a half an hour, a couple hours, go work out, do something like that, come back, your brain is rebooted and all of a sudden you can see what the problem was. And so I encourage you to do that. So 30 minutes is about where it is. Okay, now this is, we are here to help. So we are live teachers, we're people and we're here. This isn't like some YouTube video that was created 10 years ago that just happens to be still out there. We are here. So when you ask for help, we're going to jump up and try to email you and set up video calls. So you got to right away get used to using us to help you get unstuck. Okay. Cause we're here and this will be awesome. All right. That is the entire course overview and you are ready to start making progress on module 8 of the course, and good luck. I look forward to working with you this summer.